Thank you for choosing to watch this brief video to introduce two new product lines that we will be rolling out over the coming years. These products have been developed to address some clear needs that we see in the clocking market where we feel existing products and approaches do not provide a good solution. In both cases, we have silicon in our lab that is working well and that is meeting our design targets. We will be generating comprehensive test reports over the coming months, and we'd be delighted to talk with you about applying these new building blocks to solve tough problems in your system. The first product that we are introducing today is a new PLL architecture. We developed this PLL to use a minimum number of analog components. Apart from the digitally controlled VCO and the output buffers, all of the circuits in this PLL are logic gates. This has enabled us to achieve a truly impressive power performance area figure of merit, 10 times better than our previous LC PLL, and more than 40 times better than our best ring PLLs. We're currently testing silicon of this PLL in a 6nm test chip, and we'll be delighted to port this PLL to other process nodes for you. The left-hand side of this slide shows the oscillator noise simulation of the broadband jitter of the PLL generated by the VCO, with other noise contributors to closed-loop noise added using MATLAB. The VCO itself contributes less than 0.1 picoseconds of broadband long-term jitter. With generous allowances for the other noise contributors, the whole PLL is predicted to generate less than 0.3 picoseconds RMS of broadband jitter. We put this PLL onto our 6nm test chip at the very last moment, and so did not get a chance to design a low jitter clock path or output buffer. As a result, the measured performance is limited by the test chip, which shows in bypass mode 0.8 picoseconds of RMS jitter for the entire path onto the chip and off the chip. When we turn on the PLL, the broadband jitter measured drops to 0.4 picoseconds RMS, when the PLL is using less than 8 milliwatts. This indicates that the PLL's added jitter is certainly much less than 0.4 picoseconds RMS, and is likely less than the design target. It is interesting to compare this new PLL with our best ring PLL. In both cases, the common target application is to generate a reference clock for PCIe 1, 2, 3, 4, and 5 PHYs. Both PLLs achieve this, but the figure of merit for the new LC PLL is more than 40 times better. The new PLL performance is good enough for some high-end codecs as well as PCIe 5 references. The other product that we're introducing today is what we're calling a frequency generator. This product is built from a production-proven fractional NPLL. We take a copy of the locked PLL VCO current and pass that through a DAC to drive a copy of the VCO. This provides a second output, which is frequency locked to the fractional multiple of the reference clock, and can be programmed over a 2.5 to 1 frequency range before the output divider. The DAC is designed to be asynchronously programmable and settle very quickly without overshoot. While PLLs initially settle on timescales of several microseconds, and being second or third order loops either overshoot or settle very, very slowly, the DAC does not overshoot at all and settles on a timescale in the range of 12 nanoseconds. This enables dynamic frequency scaling with smaller timing margin and with frequency changes over 100 times faster than before. The frequency switching is even fast enough to detect a supply glitch and drop the logic clock ahead of the slight supply droop. We have a companion circuit that directly measures logic delay, and together with the frequency generator, can be used to automatically adjust the clock speed over PVT. We expect the same logic circuits to be able to be designed to run much faster with these building blocks. This slide shows some early measurements of our FG product or frequency generator product in a 5nm test chip. In this case, the DAC is programmed to have the output switch from 1.6 GHz to 3.2 GHz and back to 1.6 GHz. You can see here the output clock divided down to 800 MHz to get it off chip transitions both rapidly and smoothly to the target frequency. The equivalent time constant we measure here is around 7 nanoseconds, which is likely faster than a supply droop in a chip with an acceptable amount of on-die decoupling. Thank you for watching the video to learn about our new products. We're quite excited about them. If you're watching the video at a trade show and would like to learn more about them, please join a live chat in our booth and talk to one of our staff. Otherwise, feel free to send an email to our sales team and schedule a discussion with us. Thank you.